Welcome to the Deep Dive.
Hello.
Today we're diving into chemistry, really honing in on those core concepts you might see highlighted across different learning materials.
Exactly. We looked at, audio clips, textbook sections, video bits, a real mix.
And the mission is simple. Pull out the key takeaways, the essentials, to help you feel solid on the fundamentals, maybe for something like a final exam.
Let's get into it.
Okay, first up, the absolute bedrock. Measurements. The sources really hit this home.
Cool.
A measurement isn't just a number.
No, you absolutely need the unit too. Number and unit. Always.
And those numbers, they carry meaning about precision, right? That's where significant figures come in.
Sig figs. Knowing the rules, like with leading or trailing zeros, tells you how precise your measurement actually is. It matters, especially for calculations.
Definitely. And speaking of calculations, you're often converting units. The metric system is your friend here.
Oh, yeah. Grams, liters, meters,
Yeah.
the base units. The key for conversions is using those conversion factors. Sometimes drawing out a little solution map helps plan the steps.
Right, like going from centimeters to inches, or maybe something trickier like grams per pound to milligrams per kilogram. You just chain the factors.
Density is a great concept that ties this together. Mass divided by volume. Simple definition.
But it's more than just a calculation. Density itself is a conversion factor, isn't it?
Exactly. It lets you link mass and volume directly for a specific substance. Super useful.
And don't forget interpreting data visually. Like graphs showing CO2 levels changing over years, you need to read those trends.
Okay, let's zoom in. Atoms. Our understanding has evolved quite a bit.
From early ideas to things like the plum pudding model, then Rutherford finding that dense positive nucleus.
Which eventually led us to the quantum mechanical model. This is where things get a bit weird. No more neat orbits like Bohr thought.
Right, now we talk about orbitals, regions of probability, basically where you're likely to find an electron.
And inside the atom, you've got your main players. Protons, positive, in the nucleus. Neutrons, no charge, also nucleus. And electrons, negative, outside the nucleus.
Protons and neutrons give the atom its mass, mostly. Electrons are tiny in comparison.
The number of protons, that's the atomic number, defines the element. But neutrons, they can vary.
Oh, isotopes. Same element, so same protons, but different numbers of neutrons, which means a different mass number.
Yeah, and that average atomic mass you see on the periodic table, it's a weighted average based on how abundant each isotope is naturally. Neutrons might not have charge, but they are crucial for mass and stability.
And electron behavior. Electrons jumping between energy levels.
Yep, absorb energy, jump up, fall back down, emit light. That's linked to Bohr's ideas, but refined now. These levels have subshells, S, P, D, F.
Each holding a certain number of electrons, 2 in an S, 6 in a P, and so on, and they have shapes, like the S orbital is spherical.
And this electron structure is the key to understanding the periodic table. Mendeleev and others organized it based on repeating properties.
Now it's by atomic number, and its layout tells you so much. Group number often hints at valence electrons, the outer ones involved in bonding.
Period number tells you the main energy level. Plus, metals over here, non-metals there. Important families like alkali metals or halogens.
And the trends, ionization energy, atomic size, they change predictably across and down the table.
So why do atoms even bother bonding? Usually it's the octet rule.
The drive to get 8 electrons in that outer shell, or 2 for hydrogen and helium. They gain, lose, or share to get there.
Which leads to different bond types. Ionic first, typically metal and non-metal. One atom basically gives electrons to the other.
Creating ions charged atoms. Positive and negative attract strongly. Like NaCl, table salt. They're usually solid, only conduct electricity when melted or dissolved.
Because the ions need to be free to move. Then you have covalent bonds, that's electron sharing, usually between non-metals.
And that sharing isn't always equal, right? That gives us polarity.
Exactly. Depends on electronegativity differences. Big difference, it's polar covalent. Very small or zero difference, non-polar covalent. Equal sharing.
And how these atoms bond determines the molecule's 3D shape. VSEPR theory helps predict that.
Yeah, valence shell, electron pair repulsion. Electron groups push each other away. Methane, CH4, ends up tetrahedral because of it.
And that shape, combined with bond polarity, decides if the whole molecule is polar.
Which is huge. It dictates properties like whether something dissolves in water.
You also need to know the naming conventions, different rules for ionic versus covalent compounds, often using prefixes for covalent.
And beyond the bonds inside molecules, you have forces between them. Intermolecular forces.
London dispersion, dipole-dipole, hydrogen bonds, weaker than covalent or ionic bonds, but they hold liquids and solids together and affect things like boiling points. Okay, shifting gears to chemical reactions, transforming stuff.
Why do we care? Well, they power our cars, cook our food, even neutralize acid in your stomach. They're everywhere.
Basic setup. Reactants on the left, products on the right, and balancing. Absolutely critical.
You have to balance them. Law of conservation of mass. Change the coefficients, the big numbers in front, never the subscripts within a formula.
There are common patterns too, reaction types. Synthesis, decomposition.
Single replacement, double replacement, sometimes called precipitation if a solid forms. Combustion, that's burning, usually with O2. And acid-base neutralization.
Now for the math side, the mole. The chemist's dozen, but a much bigger number.
6.022 times 10 to the 23rd. Avogadro's number. It's how we count atoms and molecules practically.
And it's the bridge. You use molar mass from the periodic table to go between grams and moles. Avogadro's number links moles and actual particles.
And crucially, the balanced equation itself gives you mole ratios. That's stoichiometry, using the equation to calculate how much reactant you need or product you'll get.
We also deal with solutions a lot. Solute dissolved in a solvent.
And we need to talk about concentration. Molarity is a big one. Moles of solid per liter of solution. You calculate it, you use it in stoichiometry.
Finally, energy changes. Reactions can release heat exothermic. Think flames.
Or absorbed heat endothermic, like melting ice or vaporization. Enthalpy change tells you which it is. You can even calculate the heat transferred using QMC delta T, involving mass, specific heat capacity, and temperature change.
So quite a journey there, from measurements and atoms
Through bonding and structure.
all the way to reactions and calculations.
Meaning how these pieces connect, how particle behavior dictates large-scale properties. That's really the heart of chemistry, pulling together insights from all those sources.
Absolutely. So as a final thought to chew on, how do those fundamental, almost abstract rules governing tiny electrons and atoms manage to orchestrate the incredibly complex and tangible chemical world we experience every single day?